Okay, so this is going to be our last lecture of the semester here. And we've already talked a bit about this in lab because we did the ocean acidification lab. So I'll kind of go through the very first portion of this lecture in a more brief manner since you've already covered it in lab. But as we talked about in lab, this has become really, one of the largest problems for our generation and for our planet as a whole, one of the largest problems that we're facing in terms of the fact that climate change can have detrimental impacts and is having detrimental impacts on ecosystems all over the world, and not just marine ecosystems, even though obviously we're going to focus upon more of the impacts upon marine ecology. So your textbook actually has a whole section now. It's called a special report, and it's in the middle of your textbook. It's these kind of blue colored pages that you'll see, and they actually put together this special report on climate change, which is pretty impressive for the textbook. I'm not that I need to be impressed with the Castor and Huber textbook. I know that they're an expensive book, but there is just no other book out there for a non-majors marine biology course that does the incredible job that they do. So that's why we pick Castor and Huber for this course. Okay, so, and no, I have no affiliation for them. I just really appreciate the textbook that they've put together. So again, we talked a little bit about this whole idea of carbon cycling, and you guys are pretty familiar with this whole carbon cycle on land, and we've talked about it. Again, trees take up carbon dioxide, consumers and higher level primary and higher level consumers feed on those materials and other organisms, and as a byproduct of cellular respiration, produce carbon dioxide that then can be taken back in by these plants. And again, we talked about decomposition also again releases carbon dioxide. And so again, there's this kind of natural cycle in terms of our carbon cycle. And then we talked about the fact that now we are inputting quite a bit of extra carbon dioxide now into this cycle. And that's where the challenges come into play. Now, again, what a lot of these basic carbon cycles don't talk about is the fact that there's this whole other part of the carbon cycle that has to do with the oceans as well. So the oceans are a really big part of our carbon cycle. So to not include them would be quite silly because they take in quite a bit of carbon dioxide because our oceans can dissolve carbon dioxide within the water, as we talked about in lab. And so this is important because our oceans kind of act as this carbon sink. But as again, we're producing this excess carbon dioxide, we're kind of overloading the system. And so more carbon dioxide is being dissolved in our oceans than has ever been before in the past. And we're seeing again, we'll talk about again, the formation of carbonic acid like we did in lab, and the fact that again, our oceans are becoming more acidic. Because this excess dissolved carbon dioxide. But again, you have this nice part of the carbon cycle where that dissolved carbon dioxide, again, is important for photosynthetic organisms like our primary producers like algae, like our phytoplankton. And again, those organisms will feed your primary consumers, which feed your primary consumers, then feed your secondary consumers on up the food chain. All those organisms do cellular respiration and produce carbon dioxide as a byproduct, which dissolves back in the seawater, and again, then can be used by these primary producers. Along with, again, remember you get some carbon dioxide release from your decomposition process as well. So again, we have this nice carbon cycle that's happening in our oceans as well. So what I want to do is play this Smithsonian video. It is a great video in terms of doing this great carbon cycle animation, and it includes the oceans, which is very nice. So I'm going to go ahead and play this for you just because it does a wonderful going through the carbon cycle here. So it really and it really simplifies it as well. Again, carbon affects Earth's climate and life. Carbon is in the Earth's crust. again, in the soil, in our oceans. Carbon is also in the air as the planet-warming gas from carbon dioxide. And carbon is in all living things. Carbon is in all living things, including us. Our planet is like a great carbon machine, moving carbon around in an endless cycle. Plants pull carbon out of the air to grow. Animals get carbon by eating plants or other animals. And dead plants and animals leave carbon in the soil, returning that carbon to the soil. And when the decay process occurs, most of their carbon soon returns to the air in the form of carbon dioxide. In the same way, carbon also moves rapidly between the air and the ocean. So again, you have things like coral and algae that are taking up that carbon dioxide. But carbon accumulates in the earth very slowly as dead animals and plants become fossil fuels like coal and oil. As rocks weather, carbon moves from the air to the ocean where it combines with calcium dissolved in water and forms limestone. Volcanism returns into the atmosphere as rocks are heated deep in the earth over millions of years. This machine has chugged along with nearly balanced flows for tens of millions of years until fossil fuels. About 150 years ago, when we began to mine fossil carbon and burn it for energy. Today, we release carbon into the air more than 100 times faster than natural processes return it to the earth. Farming and cutting forests also adds carbon to the atmosphere. So carbon is rapidly building up in the atmosphere faster than ever before in Earth's history. And it shows a 42% increase. Natural processes will take many thousands of years to remove the excess carbon from the air. So more carbon in the atmosphere warms the climate, making life hard for many species, including us. Excess carbon also makes the ocean more acidic, threatening marine ecosystems and raising sea levels. It's up to us to work to stop our carbon emissions, to rebalance the cycle, and preserve our quality of life. So again, this was just a simple animation that was put together by the Smithsonian to help students understand this carbon cycle process. I thought they did a pretty nice job of kind of simplifying the carbon cycle to give you kind of the basic idea of how the carbon cycle functions and how it's out of balance right now with the excess input of fossil fuels and burning of fossil fuels. So I know we already talked about this. I know we talked about, again, we know that the carbon dioxide levels are rising. We can see that. We've been tracking that from the Mauna Loa station since 1958. So we know that our carbon dioxide levels in the atmosphere are rising. And we know that our carbon dioxide levels, based upon, again, our Antarctic ice cores, we know that our carbon dioxide levels in the atmosphere are higher than they've ever been in history. Again, you can see here the highest previous concentrations were really, just around 300 parts per million. And now we're talking about, again, we've skyrocketed well over 400 parts per million now. So again, atmospheric carbon dioxide levels have never been this high over the past 800,000 years. And so, of course, the big question is, what does that mean for us? And that's what we're going to talk about here in just a minute. So yeah, again, this is the Hawaii's Mauna Loa monitoring station data. And so again, you can see this kind of consistent rise of carbon dioxide levels, again, as we've gone from 1958 to the current time frame. And so again, we're now well over 400 parts per million. And you can see there's always these fluctuations in carbon dioxide levels annually. And again, that has to do with, the cycling of not only like phytoplankton blooms and things like that, but also then, with the seasonal changes in terms of, your flora, basically your plant life that, will thrive again in the spring and summer. And then, again, in the winter, though a lot of those plants are going dormant, not taking in as much carbon dioxide. So again, we see these annual fluctuations. So you can see these annual fluctuations are quite small, nothing like, again, this drastic increase in atmospheric carbon dioxide levels due to the burning of fossil fuels. So I like this graph in that it does show these small annual fluctuations. So again, atmospheric carbon dioxide concentrations have been tracked. And you guys actually calculated this in lab. So you calculated this number. We are seeing an increase on average of about 1.5 parts per million carbon dioxide per year. That means we're adding an extra 1.5 parts per million of carbon dioxide into the atmosphere every year. And in recent years, we've seen that this has increased at an even more rapid rate to about 3 parts per million per year. So again, today our concentrations exceed well over 400 parts per million, and the current rate of increase is 200 times faster than in the last 800,000 years. So this is why, again, scientists are concerned about our atmospheric carbon dioxide levels. And if carbon dioxide concentrations continue to increase at this current rate, by 2075, the concentration will have doubled. So what are some of the sources of our excess carbon dioxide level in the atmosphere today? A big one is the burning of trees for deforestation to clear cut land for agriculture, and the burning of fossil fuels, of course. About 80% of the increase in atmospheric carbon dioxide level, or I should say the anthropogenic. The anthropogenic means the human kind of induced increase in carbon dioxide levels. So about 80% of that anthropogenic carbon dioxide in our atmosphere today comes from the burning of fossil fuels. And some recent data showed that it's actually about 100 companies that are responsible for about 71% of the global carbon dioxide emissions, which is pretty crazy to me. So you can see, you can look at some of this data. Now, there are other greenhouse gases that we're not going to talk about just because we just don't have that much time to talk about, but please look into them. Obviously, methane's one that you've probably heard about in terms of agriculture. Nitrous oxide is another smaller percentage, but you can see carbon dioxide makes up the vast majority of the excess greenhouse gas emissions right now. And this is kind of nice. It just breaks it down by economic sector. So you can see agriculture, forestry, and land use here. And then the rest of this is kind of the burning of fossil fuels for industry and electricity, heat production, etc. And then this is kind of nice. This was from 2014, but it was just a nice little pie chart that showed, and this was from the NOAA site. It just showed kind of the breakdown of fossil fuel emissions from different countries throughout the world. And you can see again, by far your developed nations are responsible for the majority of the carbon dioxide emissions. So what's the significance of all this excess carbon dioxide and why should we care? And you guys probably are well aware of the fact that we have this thing called the greenhouse effect. Without the greenhouse effect, honestly, we couldn't live on this planet. So, the greenhouse effect is a good thing. And so much of the solar radiation that comes from the sun that strikes the Earth's surface is actually reflected back as heat radiation. And so now the challenge is that these excess greenhouse gases like carbon dioxide will again reflect back that heat radiation towards the Earth's surface. And when we had a normal level of carbon dioxide and these other greenhouse gases like methane in the atmosphere, that was a good thing, right? Because without the greenhouse effect, our planet would be quite cold. But the challenge is now that we are putting so much excess carbon dioxide and methane into the atmosphere, we are now, bouncing back even more of this heat than ever before to the surface of the Earth. And that's what's causing the increased warming of the Earth's surface. So again, much of that solar radiation strikes the Earth's surface, is reflected back as heat radiation, and then carbon dioxide, along with other greenhouse gases, even water vapor, in the atmosphere will reflect back that heat radiation. So you can see that here, methane and carbon dioxide, reflect back that heat radiation towards the Earth's surface. Again, warming the surface of the Earth and the atmosphere. So again, the challenge is not that the greenhouse effect happens because we need the greenhouse effect. The challenge is that we now have an enhanced greenhouse effect with these excess greenhouse gases now. And so you can actually go to this site and click on this site if you want a little bit more information on the greenhouse effect. But again, as we mentioned, the greenhouse effect isn't a controversial topic at all. And it's just literally a mechanism by which the Earth actually a viable place for us to live, because without the greenhouse effect, the global average temperature would only be around -4 degrees Fahrenheit. So thank goodness that we have this greenhouse effect, right? But again, the challenge today is now that we have this excess atmospheric carbon dioxide production, along with methane and other greenhouse gases, we now have this kind of enhanced greenhouse effect. And ultimately, that is what's leading to climate change today. So again, we know that the Earth's surface is warming, and we now can say with certainty, based on the last IPCC data, this is, IPCC is the Intergovernmental Panel on Climate Change, and that is a basically group of scientists from all over the world that get together to share their data on climate change and put it together in this nice, I say concise report, but it's concise based on all the information they have, right? But it's got a lot of information in it. But they put it together in this one single report so that policymakers all over the world can use this data, the most current data from climate scientists all over the world. They can use that data so that way then they can then make decisions based upon that data. And so that's what the IPCC is, this Intergovernmental Panel on Climate Change. And they just put out a report for 2022, and then they're coming up with their kind of mitigation plans. So we'll talk a little bit about that. But you can see again, this was in the last assessment report, one of the last assessment reports, actually probably 2 assessment reports ago. And you can see that we know that temperatures are rising higher than they ever have in the past. And so we know that we have, and we can see that this is directly related with the production of fossil fuels and the burning of fossil fuels. So again, there's direct correlations that we can make to those time periods. So we know that, again, the Earth is warmer than it has ever been. And so now we have this challenge of kind of understanding the difference between climate versus weather, because there is quite a bit of misinformation out there in terms of what is going on with climate change. And you'll hear a lot of people go, well, this year was a really cold winter for us, so that climate change is just silly. It's just scientists are just making it up, which you have to ask yourself the question, why would scientists make this up, right? And again, if you now know, taking a science course, that the scientific method is the base and the foundation for science. And so if you're a scientist, you follow that pretty strictly. So climate versus weather. When we look at climate is going to refer to the large-scale changes in things like temperature and rainfall. But we're looking at, again, a span of at least 30 plus years. So we're not talking about the annual changes that you might have from one year to the next, or even from like 5 years to the next 5 years. We are talking about, again, a span of 30 plus years when we're talking about average temperatures and precipitation patterns when we're talking about climate. Weather is going to be more of our short-term conditions over days or months or even over year to year. So again, you may say, oh, well, last year, we had, or this year we had a really cold winter. So, climate change must not be happening. But again, that is a change from year to year. So that's what we consider to be weather. When we're looking at our overall increases in temperature, we are looking at climate, things that are happening on a much larger scale, okay? So please try to keep that in mind as you hear information out there. And I will tell you from a biologist perspective, I hear a lot of misinformation out there, and it's quite frustrating from a scientist perspective. So is anthropogenic climate change really happening? And so we do know that the Earth is now greater than 1 degree Celsius warmer than it was before the age of the Industrial Revolution. And in the most recent IPCC report that came out, it states that we are 100% certain that human influence has warmed the atmosphere. This is what we call scientific consensus. This means that all of the scientific data that we have out there right now, when we compile all of that data, it supports this hypothesis that the 1 degree Celsius warming that we are seeing is directly related to us as humans and the production of fossil fuels and the burning of fossil fuels, along with, again, clear-cutting land and things like that. So again, this is what we call scientific consensus. The majority of the scientists, there may be a few outliers out there, but again, you're talking about the majority of the scientists out there that are doing research on climate change. The majority of them agree with 100% certainty that human influence has warmed the atmosphere. And that, to me, is a pretty significant thing. So, that's the kind of data that I pay attention to, because let me tell you, scientific consensus, that may seem like an easy thing, but no, it is not. I mean, you get a bunch of scientists in a room together and they love to be able to pick apart each other's data. That's what science is about, right? And it's good because it ensures that only good science comes out, right? Or at least for the most part. Again, there's always those exceptions, but for the most part, again, science has its own checks and balances built within it. And that helps to strengthen science. So when we talk about the Earth, again, the Earth is predicted to warm about 1.5 to 2 degrees Celsius by the year 2100 if we don't make changes now. And we will talk about this kind of trigger point. And again, many scientists cringe when they hear that 1.5 degrees Celsius warming, especially up to 2 degrees Celsius, because we know that this will trigger, and you guys now know about these down kind of stream cascade effects. So this is what we are worried about, triggering these cascades that will have impacts, and these positive feedback loops that will have impacts that are irreparable. So we'll talk about some of those. So again, there are some different perspectives on climate change, but again, many of these have been debunked. There was one that there's that climate change over the next 1,000 years would be really more due to the change in the Earth's orbit. This is called the Milankovitch theory. However, what we're seeing is that, and I actually have some data on that here. You can see the IPCC change states that the changes in the solar irradiance due to orbital changes have been estimated to cause only a radiative force of what we say is plus 0.12. I know that probably doesn't mean a lot to you, but what this means is that that is not enough of a radiative force to be causing the warming trends that we are seeing now. And when they started to look at the radiative force of carbon dioxide, methane, and nitrous oxide, all of these greenhouse gases, that was on a level of plus 2.3. So the radiative force of these greenhouse gases is much greater than that radiative force that was just responsible for these slight changes in our orbit. So that kind of debunked the Milankovitch theory. Over the next century, there were some scientists that were saying, not now, but kind of initially, that temperatures are likely to be warmer, but that natural forces were responsible for this. Things like El Nino and the something called the Pacific Decadal Oscillation, which is kind of a 10-year like El Nino type cycle. That volcanoes were going to be more responsible for, warming and again, increase in solar radiation, which we just talked about. That those were more likely to be the main factors. But as you can see, again, we see these kind of smaller fluctuations when we're talking about things like El Nino and then the Pacific Decadal Oscillation. So these are, again, just shorter term fluctuations, and we always seem to go kind of back to our kind of our 0 point in terms of just things that are responsible for warming trends by these two different kind of changes in our wind patterns. So again, this data really shows that El Nino and the Pacific Decadal Oscillation cannot account for, again, the warming trends that we're seeing today. So how do we know that rising carbon dioxide levels are associated with rising temperatures? And again, we talked about this in terms of the ice core data, so I'm not going to go over this too much because I kind of talked about this in lab. And then you saw it in the very beginning of the lecture, but you can see we have these ice core data. We talked about why, again, when, water solidifies, remember it forms that nice hexagonal pattern as it solidifies, that kind of crystalline shape, and then it traps air within it, and then we can go back and look in these ice core samples, because as the ice froze, hundreds of thousands of years ago, it trapped air inside of it, and that air is representative of the what was in the atmosphere at that time, the concentrations of carbon dioxide in the atmosphere at that time. So we can actually go back and look at the concentrations of the atmosphere at that point in time by looking at these ice core samples. And so we can see that there were always these fluctuations in terms of and these temperature fluctuations that followed the pattern of the carbon dioxide level fluctuations when we look at ice core data, and we also looked at tree core samples as well. So we can see these fluctuations. But again, there were nothing like the increase in temperature that we are seeing now. So again, you can kind of see the trend in kind of global average surface temperatures if you're going back to like 1860. And you can see again, nothing, our increase in global surface temperatures are greater than they have ever been in terms of that data. So this just is showing you more data to kind of support that, global temperatures are changing. And I think you guys probably have seen enough data on this to support this idea that we definitely are seeing, these warming trends. And it makes sense, right, in terms of if you understand the greenhouse effect. This doesn't seem abnormal. This makes, sense as a scientist on why this would happen. We are seeing now some impacts of this, and this is going to be where we're going to start to talk about what we call some of these positive feedback cycles. So you can see this is the melting of the Greenland ice sheets, and I didn't have a recent image of this, but this is kind of some older satellite imagery. But you can see here was the 1992 melt, and then here was the 2005 melt. So you can see that the Greenland ice sheet is melting, and we can use satellite data to map the extent of this snow melt. So again, we have pretty decent data on this. Now, what ends up becoming the challenge with this is if you look, right, white snow is going to reflect light, right? And we talked about this, white things reflect light. Dark surfaces, right? So if you expose the soil and permafrost below here, it's a dark surface, and just like your black shirt on a sunny day, those dark surfaces are going to take in that light, and then remember, it'll excite those molecules and then release heat as a byproduct of exciting those molecules. So the challenge is that as the Greenland ice sheet actually melts, and this happens again with any of your glacial melt, as permafrost is exposed below, then you're actually going to release more heat back to the atmosphere. So this is one of those positive feedback loops, right? So as the earth warms, right, more of that Greenland ice sheet melts. As more of that Greenland ice sheet melts, it's going to absorb and reflect more of that heat back to the atmosphere, because again, you're exposing that dark permafrost, then warming the atmosphere even more. That's going to melt the Greenland ice sheet even more, exposing even more permafrost. That's going to, again, absorb and reflect more of that heat back. Continuing this positive feedback loop. And this is what scientists start to get concerned about, are these positive feedback loops that kind of propel themselves. So again, this is what we call that positive feedback system. So I kind of go through what I just talked about here. Light colored ice reflects back the sun's energy. The exposed now, again, as land is exposed with that, glacial melt, the darker color of the soil and permafrost below is going to absorb more of that light energy. As the ice melts, more of the land is exposed, and this absorbs even more heat, melting the ice even faster. And again, the altitude of the melting ice is then reduced, so it becomes harder for new ice to form. So it's just this kind of perpetuating cycle, and we call this a positive feedback loop, where again, you're just, the effect of this initial change causes even more of that initial change to occur. So that's what we call a positive feedback loop. So again, this is just a poster. This was kind of controversial in, information initially, but then kind of was eventually substantiated by many scientists over the world. And so there was this photographer by the name of Gary Braasch, and he ended up taking images of glaciers and over the years showing glacier recession. So again, remember that glacier recession does occur every year. You're going to have slight changes in glaciers every year in terms of freezing and then recession, freezing, recession on just seasonal patterns, but not to this extent that we saw in his images. And so again, you can see that in his images, we know that we're seeing glacial recession due to climate change, and you can see some of it has been pretty extensive here. Let's talk a little bit about rising sea levels, because this becomes a challenge. When scientists first discovered that sea levels were rising, they couldn't figure out why sea levels were rising at a much more rapid rate than they had initially basically calculated for, because they had done some calculations, and based on the glacial melt, they had initially thought, okay, well, sea levels should rise this much. And when we found out the sea levels were rising even more than what we had initially kind of planned for, scientists went back and started to ask this question of, why was that? And we kind of forgot about this very basic thing that you actually know. You learned this early in this class. And this is called thermal expansion. And that's the very simple fact that when you take water molecules and you add heat energy to them, you excite those water molecules. And as you excite those water molecules, they are going to take up more space. So this is what we call thermal expansion. So not only are we getting rising sea levels due to, glacial melt, and the melting of the polar ice caps, but now we're also getting this sea level rise due to simple thermal expansion. The fact that when water is heated, the molecules are going to get excited and take up more space, and this increases the volume of water. So this is why, again, rising sea levels are happening more rapidly than we had originally anticipated. So this kind of shows you some of the older data. I didn't have any real recent data. I apologize because I need to update this in terms of our rising sea levels, but you can see they are accelerating quite rapidly. And this is definitely something that we're concerned about, especially in the coastal communities. And so I'm not going to get into this too much, but there are impacts, just because I know that this lecture is getting pretty long, and you are welcome to look into this further, but there are impacts to remember this thermohaline circulation that we talked about in terms of climate change, and really kind of the shutting down of some of these big thermohaline circulation patterns, or at least the slowing of some of these. And so again, you can see, just like when we talk about El Nino, changing some of these thermohaline patterns or cycles will really impact things like areas where we might have coastal upwellings. And so if we, again, don't have those coastal upwellings, or they're decreased, this can drastically impact, all kinds of these marine ecological habitats, especially those that are involved with fisheries. So again, this can be quite detrimental to, so the slowing of some of this thermohaline circulation, and we have seen some of this occur already, will impact us directly by impacting, our fisheries as well, as we slow down some of these upwellings. And again, remember, upwellings are associated with bringing nutrients up from the deep. And, that's what fish love. Fish love that, and that's where fish thrive, right? So those are great fishing areas. But as we slow down some of these thermohaline circulation patterns, then again, we can slow down some of those upwellings, and that becomes an issue for the fishing industry. So we talked about ocean acidification, I know, in lab, and I'll go over it just really briefly here. But again, the oceans, as we know, are responsible for absorbing and dissolving carbon dioxide, and they're actually responsible for absorbing up as much to 31% of our atmospheric carbon dioxide. So, as you well know, when, again, that carbon dioxide is absorbed, it can form carbonic acid. And when it can do this, again, it can, on a mass, global extent, in terms of, again, a lot of atmospheric carbon dioxide, right, has to be input into our oceans to raise the acidity of or lower the pH, right? The lower pH, it means more acidic, to lower the pH of our oceans. And so we are seeing that. Now, just as a reminder, our pH scale is logarithmic. So each change in pH is a 10-fold change. So again, 7 is neutral. Remember that anything below 7 is acidic, and anything above 7 is more basic. So just as a reminder, I know we did this in lab, so I'm not going to go over this again. You guys can kind of review that on your own. But what we do know is, again, we can see this process of ocean acidification and how it occurs. And again, we talked about this in lab because we did this experiment, right, where we actually took some shells and put them in an acidic environment to see what would happen to them. Now, we put them in a really acidic environment at a pH of 3, right? But we saw that pretty quickly, in just a week, we saw the breakdown of that calcium carbonate. And so that's what we're concerned with in terms of an increase in ocean acidity, is the breakdown of this calcium carbonate. And that we talked about not only the breakdown of that calcium carbonate, but the fact that making our oceans more acidic will actually bind up that carbonate. So again, calcium carbonate isn't formed, and organisms that use calcium carbonate, like coral and your mollusks like clams and snails, and even your your coralline algae, they are not going to be able to make those calcium carbonate skeletons without this calcium carbonate, this good supply of calcium carbonate. So we can see again in normal atmospheric levels, again, carbon dioxide and water form carbonic acid. And again, then we get some bicarbonate production, we get some hydrogen production. But again, there's some formation of bicarbonate, but not enough. There's not enough hydrogen ions to be binding up the majority of the carbonate right now. So carbonate can bind with calcium to form calcium carbonate, and then calcium carbonate's available for your things like your coral and any organism like a mollusk that's making a shell, right? And so those, and I should mention phytoplankton as well, because many phytoplankton have a calcium carbonate endoskeleton as well. And remember, phytoplankton are actually taking in carbon dioxide. There's a lot of phytoplankton. And phytoplankton, phyto basically, remember, means plant from lab, like plant-like. So your phytoplankton is taking in carbon dioxide, right, and doing photosynthesis. So these are the good guys, and we definitely don't want to, drastically impact the good guys of phytoplankton. Along with things like, again, coral are also taking in a lot of carbon dioxide. So are, again, your coralline algae, things like Halimata that you saw in lab, okay, are also taking in that carbon dioxide. So again, in a normal situation, there's enough calcium carbonate available for these organisms. However, when we see an excess input of carbon dioxide, right? So carbon dioxide levels go up. Then we're going to see an excess production of carbonic acid. That carbonic acid, again, like we talked about, is going to separate into bicarbonate and hydrogen ions. Hydrogen ions are, again, what increase the acidity or lower your pH. So lower pH, increase acidity. And then what we see is more of these hydrogen ions binding to this carbonate and basically kind of stealing that carbonate and storing it in this form of bicarbonate. So the challenge with that then is there's less carbonate available to make calcium carbonate, which means there's less calcium carbonate. So less calcium carbonate means thinner shells and dead coral, okay? Because they don't have that calcium carbonate, and we are seeing that already. So again, the consumption of carbonate ions really, as they say here, impedes calcification, prevents calcification. And this ends up creating this kind of positive feedback loop that I talked about, where as we get an increase in acidification, ocean acidification, there's less calcium carbonate available for things like your phytoplankton, right? And literally they're seeing this. I went to a talk with a U of A scientist who was looking at phytoplankton populations, and she was already seeing the impacts of ocean acidification on this phytoplankton. So if we decrease then because of ocean acidification and there's not enough calcium carbonate available for our phytoplankton, right? Then we have a lower phytoplankton population. As our phytoplankton population lowers, there's less phytoplankton to take in carbon dioxide and do photosynthesis, right? So this is going to increase the carbon dioxide levels in the atmosphere even more. Now amplifying this whole cycle all over again. So again, fewer phytoplankton to take in carbon dioxide means more carbon dioxide in the atmosphere, which means more ocean acidification, which means a larger decrease in phytoplankton population. And so again, you can see how these positive feedback cycles kind of perpetuate themselves. And this is truly what scientists fear and are concerned about in terms of climate change. So there's this great video. I know I'm kind of going for you guys to
By now you've heard that the way we're living is filling up our atmosphere with carbon dioxide. As a result, the planet's warming. Heat waves and floods are more likely to be extreme, and people's lives will get tougher. And the more we learn about climate change, the more risks we uncover. Since we started burning fossil fuels, the ocean has absorbed about half of all the CO2 we humans have put out. That's why it's called the planet's biggest carbon sink. Now, this is good because it's kept a lot of CO2 out of the atmosphere. But as the ocean warms, it takes up less and less CO2. And with all that CO2 in the sea, scientists are shedding light on, well, an ocean of problems. Ready for the first big problem? Some sea creatures like clams, oysters, and coral, their shells and skeletons are getting weaker. Okay, you've got bigger problems than easy-to-crack clams? Maybe not if you're among the 1 in 7 people who get most of their protein from seafood, or if you understand how unstable the world would be with a billion more hungry people. What's weakening the shells? Well, these little creatures are going about their lives scooping up molecules called carbonate ions to be the building blocks of their shells. But when CO2 reacts with seawater, it releases hydrogen ions, which compete with shells for carbonate. With more hydrogen ions floating around in the ocean, our little friends have to spend more energy building their shells and have less energy for finding food. That means it's harder to grow, and more will die off before they get big. So the fish that eat the clams or live among the coral will have a harder time surviving, meaning the fish that dine on them won't have enough to eat, and so we won't have enough to eat. Remember those pesky hydrogen ions generated by more CO2? They don't just take away the carbonate ions that these little clams need. They also make the ocean more acidic. It's already become 30% more acidic since we started spewing all this CO2, and it could get much worse. We could change the ocean's chemistry so much that shells actually start to dissolve. That means if we don't turn this problem around, your great-grandkids might think of reefs the way you think of a dodo bird. And with 1 in 4 ocean species living in coral reef ecosystems, weaker coral could threaten the foundation of the whole ocean food chain. But why panic, right? Life always seems to find a way to adapt, but it needs time. In a few decades, we might make the oceans more acidic than they've been in 20 million years. It's hard to imagine any ecosystem quickly adapting to that big of a change. But things don't have to get that bad. We've started this problem, and we're going to fix it, beginning at its source, carbon dioxide from burning fossil fuels.
Okay, so I like this video. I'm going to go ahead and put it back in here because it kind of shows you at the level a little more information in terms of going through the actual chemical process. And I mainly showed you this chemical reaction because I wanted you to see how this happens, but I in no way, shape, or form expect you to know this chemical reaction for the exam. If I was going to do a question on this, it would definitely be an extra credit question. I more want you to understand the impacts that ocean acidification would have in terms of binding up that carbonate, so there's less calcium carbonate available. And then I want you to understand this kind of whole idea of this positive feedback system, meaning ocean acidification means less calcium carbonate available, means a decrease in your phytoplankton population, which many of them have that calcium carbonate endoskeleton, which again kind of is propelling this effect of even more carbon dioxide in the atmosphere. So those are the basics that I want you to understand from that whole slide. So I don't want you to get bogged down in the actual chemical equations of that or to freak out too much. And then I just wanted to show you this graph. We do actually have some documentation showing that our oceans have become more acidic. Again, this may not seem like much of a change in pH, but please remember that our pH scale is logarithmic. So any change in pH here is again a little bit more drastic than what we may think, because a change of just 1 on the pH scale is again a 10-fold change. So we are seeing some impacts, and we call this osteoporosis under the sea. So again, there was this U of A scientist, and she was looking at phytoplankton and the impacts of ocean acidification on the phytoplankton. And you can see some of the impacts to the endoskeletons of this phytoplankton, and that ends up being what's detrimental to the phytoplankton populations. We see that we can see that lower pH. So again, an increase in acidity will also start to break down and dissolve some of these calcium carbonate shells, especially on some of your smaller organisms like your zooplankton and things like that. So we definitely can see some of the downstream impacts of ocean acidification, and you guys kind of got to see a little bit of that in terms of we sped it up quite a bit in terms of using a really acidic solution to show you that in lab. So again, as carbon dioxide dissolves in the ocean and we see the increase in acidity in the ocean, not every organism is going to suffer. There are some organisms that are much more adaptable. They just may not be the organisms that, we prefer to eat. So jellyfish are kind of what we call the cockroaches of the ocean, and they tend to really do quite well in terms of if conditions change in their environment. They seem to adapt pretty rapidly. And so we may see that some species in the food web benefit while many others decline. But obviously coral, again, would be heavily impacted by that. And we're seeing that impact in terms of the increase in temperatures as well as ocean acidification on our coral reefs. So again, these are, I'm not going to go through these. You can kind of read some of these. This is some of the terrestrial impacts. And so, my last few slides are, so the planet gets a bit warmer. What's the big deal, right? And the challenge is that we will have to see and adapt to and deal with shifts in species distributions. We may see, that species that once, were limited to certain areas may now overlap with humans. And so we're seeing this again with polar bears. Polar bears now, because of the melting polar ice caps, are shifting some of their, some of their prey interactions and are feeding on other organisms and feeding kind of lower down into and when you talk about like globally in latitude, they're feeding in some of these lower latitudes now that are overlapping with humans. And so there has been an increase in polar bear attacks on humans. So again, we're seeing some of these shifts in species distributions already. Melting of the polar ice caps again is a challenge, which could ultimately result in rising sea levels. And obviously, rising sea levels don't just have to do with the melting of polar ice caps now. We have to also deal with this thermal expansion problem. Loss of biodiversity, we're already seeing, okay? So mass coral bleaching, we've already seen. And so we, are already experiencing some of the loss of biodiversity. And so you may say, well, so what? So I don't go diving. I don't really care about coral. And again, you may say that. I of course, feel quite differently. But you may say, well, coral they don't really impact me. However, you have to remember that these coral reefs are these biodiverse hotspots. And so many of our fish, many of our commercially valuable fish rely on these biodiversity hotspots and fish within these biodiversity hotspots. So again, that a reduction in those habitats, it will have massive economic impacts for us as well in terms of the fishing industry, in terms of tourism and things like that. Altered currents and more extreme storms. And also the fact that mass coral bleaching, also remember coral take in carbon dioxide too. So again, if you're not near a coral reef community, you might not realize that those coral are really valuable to you in terms of they're a big carbon sink. They take in lots of carbon dioxide level. They're carbon dioxide. They're kind of like our tropical rainforests. So losing your coral reefs are like losing some of your tropical rainforests. Altered currents and more extreme storms. Again, we're already seeing increases in disease, pests. We're already seeing loss of habitat. We're seeing. So what can the new IPCC 2020 report tell us? And so I'm just going to let this brief because of course I am never brief, and I apologize about that. But I'm going to go ahead and let this video go ahead and fill you back here, because they actually do a great job of kind of covering the 5 major things to know about the IPCC's latest 2022 report. There's that 1.5 degrees Celsius kind of flag, warning flag for us. And remember that thawing of permafrost is one of those positive feedback cycles. This is a big push in the new IPCC report. I'm going to pause that there. So if you go back to this, this is a big push, and this is going to be a big part of the mitigation plan that will be coming out in another few months here. And they're really going to push for the restoring, what they call it rewilding the wild, but restoring some of the world's damaged ecosystems that, again, are acting as these carbon sinks, pulling in carbon dioxide. So restoring some of these habitats that can really absorb a lot of carbon dioxide for us. So this will be kind of a big push in the mitigation plan for from the IPCC coming out in just another 3 months. So again, you can find this report, the IPCC report. I actually have links for you to the IPCC report on Canvas, and so you can actually go to and check out. Although I will warn you, they are quite extensive. Even though they're summary reports for policymakers, we're talking about still hundreds of pages on these reports. So again, what was my point in giving you all of this information? It wasn't to, leave you with this depressed, sad feeling and hopeless feeling. Actually, just quite the opposite. What I like to do is educate you on the information that we have as scientists. For a long time, I think that as scientists, we had this information but didn't know how to properly share it. And now that we have this information, and because there is so much misinformation out there, I felt like it was very important to share the science that we see as scientists with you, so that you have that same information and you can make decisions based upon this information. You can now make educated decisions based on this information here. So again, this was actually from the IPCC report back in 2007, and they said that the warming of the climate system is unequivocal, as is now evident from observations of increases in global average air and ocean temperatures, widespread melting of snow and ice, and rising global sea levels. So again, we knew back in 2007 that climate change, again, was occurring, and there is no debate any longer that climate change is absolutely occurring because of anthropogenic effects, because of human-induced causes. So please keep in mind that with this, science, there's a challenge with science, and that science can only tell us how the world is, but it can't tell us how the world should be. It just tells us what's happening and what is. It is ultimately up to you and your policymakers to decide that second part. And so in terms of what can you do? What can you do is, be selective in terms of these policymakers that you're voting in. make educated decisions upon those. And you can do that by simply registering to vote, and being informed and making informed voting decisions. Also, you can watch Dr. Whitcomb's presentation. He has a great presentation on kind of climate change. It's more of a civic presentation on climate change and what you can do in terms of if you want to make changes for climate change and how to get involved. And one of the websites that he suggests and actually I've had this suggested not only to me by Dr. Whitcomb, but also by someone I know that has a sustainability company. And this is one of the big websites that they advertise in terms of getting involved. If you so choose to. And again, obviously you can simply reduce your uses of fossil fuel by conserving energy. Again, do simple things, turning lights off, driving less, those types of things. Also reducing food waste and eating lower on the food chain. So again, you can make choices in terms of, you buying products that have less food packaging or have more sustainable food packaging. And then also, again, eating lower on the food chain, because agriculture and farming, we didn't get into that so much, but has a large impact in terms of clear cutting land, as well as the actual farming practices produce a lot of greenhouse gases. So again, eating meat, which is higher up on the food chain, has a larger impact on climate change than eating, again, a more vegetable-based diet. So again, you can kind of do some research into that. I'm just giving you some ideas here. Again, there's alternative fuel sources, hybrid vehicles, things like that. And then also try to keep in mind that every time that you choose to buy a product, you're making a vote for that product. You're making a vote for how that product was made, how sustainable that product is, and you're also even making a vote for how it's packaged and how sustainable that packaging is. And if you like that product, but you really don't like the fact that they use this unsustainable packaging, call the company and say, hey, and if there's enough people that call the company and say, hey, I really don't like your unsustainable packaging, then they're much more likely to make a change. Also, I'm going to hand out the Seafood Watch cards for you. And it talks about sustainable fisheries, and you can make choices in terms of if you are going to eat fish, eating more sustainable fish that are fished more sustainably. So you can make those choices as well. And then you can also make choices, again, to buy products that are used products. So you can, buy secondhand clothing and things like that. So again, those are all just some ideas for you in terms of things that you can do in terms of, your own changes. But there are many more ideas. So if you are really interested, you can go to this drawdown.org site and really get more involved. And then, of course, just the 3 R's: reduce, reuse, and recycle. So again, just a couple last minute slides for you, and one last quote to leave you with. And this was from the Apollo astronaut, where we really started to think about our planet in terms of it being, a biosphere and home for us as living organisms. And so Rusty Schweickart, this Apollo astronaut, looked back at the Earth and said, on that small blue and white planet below is everything that means anything to you. National boundaries and human artifacts no longer seem real. Only the biosphere, whole and home of life. So that is my lecture for you on climate change. If you have any questions or concerns, please feel free to let me know, as always, and I am happy to answer any questions that you may have, or look up any answers in terms of the climate change. Information is changing quite rapidly these days. So I hope that you've enjoyed the lecture, and like I said, I'm happy to answer any questions for you.